Problem 347. Two steel springs arranged in series as shown support a load P. The upper spring has 12 turns of 25 mm diameter wire on a mean radius of 100 millimeters. The lower spring consists of 10 turns of 20 mm diameter wire on a mean radius of 75 millimeters. If the maximum shearing stress in either spring must not exceed 200 megapascal, compute the maximum value of P and the total elongation of the assembly. Use equation 3-10 and modulus of rigidity equals 83 gigapascal. Compute the equivalent spring constant by dividing the load by the total elongation. Okay, so if we call this our spring number 1, this as spring number 2, we're given the number of turns, wire diameter, and mean radius of each of the springs. So let me just write the given values. And also, the modulus of rigidity is the same for, that's 83 gigapascal. And the allowable shearing stress for either spring should be less than or equal to 200 megapascal. Some student would make a mistake of thinking that P is equal to P1 plus P2, where P1 is the resisting force for spring 1 and P2 is the resisting force for spring 2. Okay, so this is not correct. This is wrong. So the right way is to cut a section, let's say here, and determine P sub 1. So if we cut a section there, we will have this for our free body diagram. Here's the load P, and here's the resistant force P1. So for equilibrium, it's obvious that P1 is equal to P. And if we cut a section here for spring 2, so what we have will be this. Here's our P, and this is spring 1. It's not cut. And there's our spring 2. So we have a resisting force P2 here. And from equilibrium, P2 is also equal to P. So according to the problem, we are going to use equation 3-10. That is the equation for heavy springs considering the curvature of the spring. And it is shearing stress equals 16 times P times R divided by pi d cube times 4m minus 1 divided by 4m minus 4 plus 0.615 divided by m, where our m is equal to 2r over d. So for spring 1, our shearing stress, will use the maximum allowable of 200 equals 16. P sub 1 is equal to P, so let's just use P. R sub 1 is 75, then divided by pi, D sub 1 is 20 cube times 4m. So we don't have m yet, so let's solve for m. M1 equals 2 times R1, 75 divided by the diameter 20 equals 7.5. So that's 4 times 7.5 minus 1 divided by 4 times 7.5 minus 4 plus 0.615 divided by 7.5. So we'll have a value for P. That's 200 times pi times 20 cube divided by 16 divided by 75 divided by the quantity 4 times 7.5 minus 1 divided by 4 times 7.5 minus 4 plus 0.615 divided by 7.5 close parentheses equals 3,498.28 newtons. Then for spring 2, our M2 is 2 times R2 is 100 divided by diameter of 25 equals, so this is 4 times 2 is 8. So again, using the maximum allowable shearing stress, 16 times P2, and P2 is equal to P times diameter of or main radius of 100 divided by pi times diameter of 25 cube times 4 times 8 minus 1 divided by 4 times 8 minus 4 plus 0.615 divided by 8. P equals 200 times pi times 25 cube divided by 16 divided by 100 divided by the quantity 4 times 8 minus 1 divided by 4 times 8 minus 4 plus 0.65 over 8 close parenthesis. P equals 5,182.29 newtons. So which is the correct answer for P? That would be P equals 3,498.28 newtons. So if this assembly is going to fail, it would be spring number 1. This one. Once P reaches 3,498.28, spring number 1 will fail. So P will not go past this value. That means this 5,182.29 is not the maximum value, but the 3,498.28 newtons. For deflection, it's obvious that the total deflection, is the total of the two deformation or deflection or elongation using the value for P, which is 3,498.28. Now, since deformation is 64 times P times R cubed times N divided by G divided by D to the fourth. So total deformation is for spring 1, that's 64 times P, we will use the maximum 3498.28 times main radius for first spring is 75 cube, number of turns is 10 divided by G, 83 gigapascal times 1000 to make it megapascal divided by D to the fourth, or the diameter, which is 20 to the fourth power, plus the second spring, the same P, main radius is 100 cube, number of turns is 12 divided by G, 83, changed to megapascal, divided by diameter of 25 to the fourth power. So total deflection is 64 times 3,498.28 times 75 cube times 10 divided by 83 divided by 1,000 divided by 20 to the fourth power plus 64 times 3,498.28 times 100 cube times 12 divided by 83 divided by 1,000 divided by 25 to the fourth power is 153.99 millimeters. And then lastly, we are going to compute the spring constant. The spring constant, let's say it's K, is equal to the load divided by the total deformation. Load is 3,498.28 divided by the total deformation. K equals 22.72. This is Newton per millimeters. Okay, so our answers are the maximum P is this one, total deformation is this one, and the spring constant is this one.